keeping information safe in our hyper-connected world, it sometimes feels like we're in this never-ending race, like we're constantly trying to stay one step ahead.
Yeah, it's like a digital arms race.
And the crazy thing is, the digital locks we depend on every day, they're basically all built on math.
Right. Super complicated math, of course.
It's still just math. And what if someday some supercomputer comes along that can actually crack that math?
That's the risk, right? The underlying vulnerability. I mean, conventional encryption, it's incredibly powerful, but it all comes down to the limits of computing power right now. As technology gets better, stronger, faster, those limitations could disappear.
So that's where this idea of quantum key distribution, QKD, comes in. And this isn't just about adding another layer of code or anything like that. This is about using the actual laws of physics, like the fundamental laws of the universe, to make communication secure.
Exactly. It's about security that's not based on just how complex something is, but on the very nature of reality.
Wow. So instead of trying to outsmart hackers with more and more complicated math, we can actually use the laws of physics to our advantage.
Right. QKD uses these kind of bizarre but very well-established principles of quantum mechanics. Things like the Heisenberg uncertainty principle. That one basically says you can't perfectly observe a quantum system without messing it up in the process.
Like if you try to look too closely at something, you accidentally change it just by looking.
Exactly. And then there's the no cloning theorem. That one states that you can't just make an exact copy of an unknown quantum state.
So you can't just duplicate a quantum key without anyone knowing.
Right. And what that means for security is that if somebody tries to eavesdrop on a quantum communication, they're going to leave a trace. They can't help but disturb the system.
That's pretty amazing. But when we talk about securing communication across the whole planet, well, things get a little more complicated, don't they? I mean, we can't just run fiber optic cables everywhere.
You're right. And sending quantum signals through the air over huge distances has its own set of challenges.
Yeah, exactly. So what are those limitations? What are we up against here?
Well, with the fiber optic cables, the problem is that the signal weakens over long distances. And to get around that, you often need these things called trusted nodes to boost the signal. But those nodes, they can be weak points, security risks, someone could tamper with them.
So they're not really as trusted as we'd like them to be.
Right. And then if you try to send the quantum signals through the air, well, you run into problems with atmospheric turbulence, like the way air moves and distorts things. And then there's just the curvature of the Earth itself to deal with.
So even with powerful lasers, it's hard to shoot a signal in a straight line over long distances because the Earth curves away.
That's right.
So that's why this new research we have is so exciting, because it looks like they've made a real breakthrough in satellite-based QKD. It seems like they've managed to make a much smaller quantum microsatellite system, and they've actually tested it, right?
Yeah. And what's really important here, and I think what's going to blow your mind, is just how much they've miniaturized things. Because that opens up a whole new world of possibilities for deploying a global quantum network. It's really some ingenious engineering work that has overcome some major hurdles.
All right, so let's back up for a second. What were those big challenges that were making it so hard to scale up satellite quantum communication before? What was standing in the way?
Well, the main thing was just trying to create a whole constellation of quantum satellites, a network of them. It was really hard to make that a practical reality.
Right, because the MISSIS satellite, that was a huge achievement, proving that space-to-ground QKD was even possible.
Yeah, but it was a huge satellite, very complex. It was like a scientific instrument, really, and it needed these massive, sophisticated ground stations to work. Plus, it could only generate secure keys relatively slowly.
So less like a quick, agile security guard and more like a big, slow-moving fortress. Hard to deploy quickly or adapt to different situations.
Exactly. If you want a global quantum network that's always on, ready to go, you need a lot of satellites and ground stations that you can easily set up in all sorts of places.
Yeah.
And the MISA system, because of its sheer size and weight, just wasn't practical for that kind of widespread deployment.
It would be like trying to build a global network of airports using only giant jumbo jets. Not very flexible.
Right. We needed something smaller, something more portable.
So that's where this Jinan-1 microsatellite enters the picture, and it sounds like a massive improvement in terms of making this technology more manageable.
It really is. The Jinan-1 is a huge step towards having these practical quantum satellite constellations in the future. Think about it. The payload, the actual equipment needed for QKD, weighs just 23 kilograms.
23 kilograms? That's incredibly light.
It is. especially when you compare it to the Mishas, which had a payload of around 250 kilograms.
That's over 90% lighter.
Yeah, it's amazing. It's like the difference between a big washing machine and a small suitcase. And the ground stations, they've also been shrunk down dramatically.
Right, because I remember those ground stations for Missus, they were huge.
Enormous. They weighed something like 13,000 kilograms each.
Wow, that's bigger than a school bus.
It is. But the portable ground stations for the GN1, they only weigh about 100 kilograms. So that's over 100 times lighter.
Wow, that's a huge difference.
Yeah, it's incredible. Something that used to need a whole building can now be moved around and set up almost anywhere, even in cities or up in the mountains.
So that makes this technology so much more accessible, right? It opens up so many more possibilities. And GN1, this isn't just a concept or a design, it's actually up in space, isn't it?
Yes, they launched it successfully in July 2022. It's in a sun-synchronous orbit, about 500 kilometers above Earth. And that kind of orbit is really useful because it means that the satellite passes over the same parts of the Earth at roughly the same local time every day. So it's very consistent.
So great, it's smaller, it's lighter, and it's actually orbiting the Earth. But how did they make everything so much smaller without sacrificing performance? What were the big technological breakthroughs that made this possible? Because I have to imagine that shrinking down all that equipment to such a small size, that must have been incredibly challenging.
Yeah, it was. There were several key innovations that made it possible. One of the most important was the quantum key distribution light source. They managed to develop this very compact, efficient QKD light source that uses just a single laser diode and some really clever external modulations.
Okay, I'll be honest, laser physics isn't exactly my strong suit. Can you break that down for me, explain it in a way that, someone like me can understand?
Sure. Imagine you need different colors of light for a specific job, but instead of using a separate flashlight for each color, you figure out a way to use just one flashlight and a bunch of filters and lenses to create all the colors you need. That's kind of what they did here.
So instead of needing a whole bunch of lasers to make the different quantum signals, they found a way to use just one laser and some fancy optics to get the job done.
Exactly. And that simplification is really key for making the whole system smaller and more rugged, especially for something that has to operate in the harsh environment of space.
Makes sense. But how did they make sure that single laser could produce all the different signals they needed?
They used this clever optical setup called a Sagnac interferometer. It's basically a way to very precisely control the properties of the light, like the intensity, that's how many photons or particles of light are emitted, and the polarization, the direction the light wave is vibrating. And this design is known for being super stable, and it lets them generate quantum signals really, really fast.
So they can crank out those secure keys faster, right?
Exactly. And when they tested this light source back on Earth, it performed amazingly well. It had this thing called a high extinction ratio, which basically means it could very clearly switch between sending a photon and not sending one, which is super important for encoding information. And it also had a high polarization contrast ratio, which means it could reliably encode information in the polarization of the photons. So it worked beautifully.
Okay, so they've got this really good, efficient quantum light source. But even if you have a perfect signal, how do you aim it accurately? How do you point that tiny satellite at a ground station hundreds of kilometers away while both are moving at crazy speeds?
That's a really good question, and this is where things get really mind-blowing.
I bet. I mean, it's one thing to generate a signal, but if you can't point it in the right direction, what good is it?
Exactly. It's a huge challenge, especially with a small satellite that's moving fast and relatively small telescopes. The one on the satellite is 200 millimeters across, and the one on the ground is 280 millimeters. The traditional way to do this, called acquisition, pointing, and tracking, or APT, uses these big, heavy mirror systems to make coarse and fine adjustments. But that wouldn't work here. Too big, too bulky.
So they had to get creative.
Yeah, they had to come up with a whole new approach. And what they did was really ingenious. They used the satellite's own attitude control system, the system that controls its orientation in space, for the initial rope tracking.
So instead of needing a separate system just for pointing, they leveraged the satellite's existing ability to orient itself.
Right. It was a way to save a lot of weight and complexity. But of course, the satellite's regular attitude control isn't precise enough for quantum communication. You need much finer control than that.
So what did they do? How did they achieve the level of precision they needed?
This is where it gets really cool. They took the uplink beacon laser from the ground station's tracking camera, and they integrated it into the feedback loop of the satellite's attitude control system. So they're using the ground station's laser as a guide beam, something for the satellite to lock onto and follow. And this lets them make tiny adjustments really fast, up to 20 times per second.
So the satellite's using the ground station's own light to help it aim more accurately.
Exactly. It's like a dance between the two. But of course, you have to think about what happens when the ground station's view is blocked, like by clouds or bad weather. The signal from the tracking camera might get interrupted. So to make the system more reliable, they built in this dual source system. If the signal from the tracking camera is lost, the satellite can seamlessly switch over to using star sensors to keep itself oriented correctly, so it can keep pointing accurately no matter what.
That's some really smart engineering. And how accurate were they able to get with this new system? How well could they actually aim?
The results were really impressive. The error range for the attitude control was way down, something like 280, 350 microradians. That's compared to 2.0, 3.0 milliradians for the Mices. And then the final tracking precision, how steady they could keep the laser pointed, that was incredibly good. Something like 0.55, 1.6 microradians for the satellite, and 3.3, 4.0 microradians for the ground station. More than enough accuracy for both the quantum signals and the regular communication.
Wow, that's amazing precision.
It is. And there's one more thing about the pointing that I think you'll find really cool.
Go on.
It's this idea of pre-pointing. Because remember, the satellite is moving so fast compared to the ground station. So you can't just aim directly at the ground station. You have to aim slightly ahead of it to where it's going to be by the time the photons arrive. And they do this, they figure out where to aim by calculating it based on the relative speed of the satellite and the ground station. And they're constantly adjusting the aim of the tracking camera. So it's very dynamic.
So it's like leading a target, aiming ahead of where it is now so you hit it in the future.
Exactly. And they did all this without needing a separate, dedicated piece of equipment for the pre-pointing, which, again, saved weight and complexity.
So to recap, we've got this much better light source, a much more efficient and precise tracking system, and a whole lot of weight savings. What other innovations were crucial for shrinking this technology down and making it work in real time?
Well, another huge part of it was figuring out how to handle both the quantum communication and the regular classical communication at the same time. Because you need that regular communication to coordinate the key exchange and control everything.
Yeah, that makes sense. But I imagine that mixing those two types of signals, the quantum and the classical, wouldn't that be tricky? Wouldn't they interfere with each other?
It could be, but they solved this really elegantly. They integrated bidirectional optical communication, meaning they can send data back and forth using an 812 nanometer laser for sending data down to the ground and a 1538 nanometer laser for receiving commands and data from the ground. And both of those operate at 156 megabits per second, which is pretty fast. And all of this is happening alongside the 850 nanometer laser used for the quantum signals.
So it's like running a regular internet connection at the same time as sending these super sensitive quantum signals.
Exactly. And to keep everything separate, they use something called wavelength division multiplexing. It's kind of like sending different radio stations over the same cable, but each one is on its own specific frequency so they don't interfere. It's the same idea here, just with light instead of radio waves.
So they're sending different signals on different wavelengths so they don't overlap and mess each other up.
That's right. And they also had to make sure that the 850 nanometer quantum light was dimmed down to the single photon level, which is essential for QKD. And they did that with a special attenuator that can reduce the strength of the quantum light without affecting the classical communication lasers.
So it's like having a very quiet whisper and a loud conversation happening at the same time, and somehow the whisper doesn't get drowned out.
Exactly.
Yeah.
And another cool thing is that because the beam of light from their telescope is so narrow and focused, they didn't even need a high-power optical amplifier for the downlink laser, which, again, saves energy and weight.
It's amazing how they've optimized every single component. But what about synchronization? How do they make sure that the satellite and the ground station are perfectly in sync? Because if the timing's off, even by a tiny bit, I imagine the whole system would fall apart.
Yeah, synchronization is critical. And they came up with a really precise way to do it. They basically embed specific timing patterns within the downlink laser signal. And by analyzing those patterns at the ground station, they can achieve synchronization accuracy of about 100 picoseconds. That's 100 trillionths of a second.
Wow, that's mind-bogglingly precise. And that lets them do what?
That incredibly precise timing means they can use a very narrow temporal gate, just 800 picoseconds wide, at the detectors on the ground that are receiving the photons. And that narrow gate acts like a filter, blocking out a lot of the background noise that could otherwise overwhelm those faint quantum signals.
So it's like they've got this incredibly sensitive listening device, and that super narrow window of time helps them focus in on the specific signal they're looking for, blocking out all the distractions.
That's a great analogy.
So we've covered a lot of ground here. More efficient light source, better tracking, clever multiplexing, precise timing. But ultimately, all of that is in service of generating those secure encryption keys. And we need to be able to do that quickly, in real time, right?
Absolutely. And that's where the real-time key distillation process comes in. They developed a 6-step procedure for this that's remarkably fast.
Okay, what are those 6 steps?
Well, first, they generate truly random numbers on the satellite. Then they send out the photons, those quantum particles of light, and measure them. After that, they use that regular communication channel, the one we talked about earlier, to exchange information about those measurements.
So both sides, the satellite and the ground station, can compare their results and see what matches up.
Right. And then they correct any errors that might have happened during transmission. That's step 4. Then they do something called privacy amplification, which basically makes the key even more secure by removing any potential information an eavesdropper might have gotten. And finally, they authenticate the shared secret key to make absolutely sure it's legitimate and hasn't been tampered with.
6 steps, and all that happens while the satellite's overhead.
Yep. And they've really streamlined the process to make it as fast and efficient as possible. For example, they use really fast physical random number generators on the satellite. These things can generate random numbers at a rate of 5 billion bits per second.
Wow, that's fast.
It is. And for extracting that secure key from the raw quantum measurements, they use some really sophisticated techniques, these decoy state QKD analysis methods. They're specifically designed to deal with the limitations of having a limited number of photons and potential fluctuations in the laser intensity. So it's very robust.
Okay, so it sounds like they've got a really solid process, but does it actually work? Were they able to generate a useful number of secure keys in their tests?
Oh yeah, the results are really impressive. In one of their tests back in September 2022, they had the satellite pass over Jinan, and during that single pass, which only lasted about 6 minutes, they were able to generate and share 406,784 bits of secure keys, all in real time.
So in just 6 minutes, they created enough secure key material to encrypt a significant amount of data.
Right. And the quantum bit error rate, the QBER, which tells you how many errors occurred during transmission, was really low, somewhere between 0.76% and 1.79% for packets of 100,000 bits.
So a very low error rate. That's good.
It is. And they didn't just do this test in Jinan. They took their portable ground stations to different locations all over the world, and they were successful everywhere. They did tests in Hefei, Wuhan, Beijing, Stellenbosch in South Africa, and even in the mountains in Nanshan. The most secure key material they generated in a single pass was actually over 1 million bits in Stellenbosch back in October 2024.
Over 1 million bits in a single pass. That's a huge leap forward. So let's talk about what we can actually do with this technology. Why should someone listening to this be excited about this? What are the real-world applications?
Well, one really cool thing is that this microsatellite can act as a sort of space postman, securely delivering encryption keys between 2 ground stations that are really far apart, even if they don't have a direct line of sight or a secure connection on the ground. And the time it takes to exchange a key is surprisingly short, only about an hour and a half.
So instead of physically transporting sensitive data, which could take days or even weeks, and is much more vulnerable to interception, you could securely transmit the keys needed to encrypt that data in a fraction of the time.
Exactly. It's a game changer for secure communication over long distances. And to prove that this works, they even did a test where they created a secure encryption key between ground stations in China and South Africa over 12,900 kilometers apart.
That's almost halfway around the world.
It is. And they use that key to do something called one-time pad encryption, which is considered to be unbreakable if done correctly. They encrypted images with this one-time pad, and it worked perfectly.
Intercontinental, ultra-secure communication, that's incredible. And the fact that these satellites are so much smaller and presumably cheaper to launch means it's actually feasible to launch a bunch of them, right? To create a real global network.
Absolutely. Imagine a whole network of these microsatellites all working together to provide secure communication anywhere on Earth.
And they could even be integrated into existing systems, right? Like space stations or the satellite internet constellations that are being built.
Exactly. They wouldn't have to build a whole new network from scratch. They could piggyback on existing infrastructure, which would make deployment so much faster and easier.
So it seems like the future of secure communication is looking very bright, but Are we done? Is this the ultimate solution, or is there still room for improvement, for even more innovation?
Oh, there's always room for improvement. The researchers who developed this system, they've already identified several areas where they want to focus their efforts going forward. One big area is creating even smaller and more efficient QKD light sources. They're looking at developing those on silicon chips, which would reduce the size, weight, and power consumption even further.
That's amazing. What else are they looking at?
Another big challenge is figuring out how to do QKD during the daytime. Right now, sunlight interferes with the quantum signals, so they can only really do this at night. But if they could solve that problem, it would be a huge step forward.
It would make the system even more versatile.
Right. And they're also exploring different ways to arrange the satellites, using different orbits and altitudes, to get the best possible coverage and performance. And then there's research into new and even more secure QKD protocols, things like measurement device independent QKD and twin field QKD. These are protocols that have some really interesting advantages for security and for extending the distance over which you can generate keys. So there's a lot of exciting stuff on the horizon.
It sounds like the field of quantum communication is just getting started.
It is. It's a really exciting time to be following this technology.
So to sum it all up, what we're seeing here with this Gene-in-1 microsatellite is a huge step towards making global secure quantum communication a reality.
Absolutely. The key takeaways are the miniaturization, how they've made everything so much smaller and lighter. Then there's the real-time key exchange and distillation, how they're able to generate and share those keys quickly and efficiently while the satellite's overhead. And finally, the fact that they've actually demonstrated intercontinental secure communication using this system. It's amazing progress.
It really is. And it makes you think about the world a little differently, doesn't it? I mean, imagine a world where communication is truly secure, guaranteed by the laws of physics, not just by complicated math that could be broken someday. What would that mean for finance, for government, for personal privacy, for international relations? What new possibilities would it open up, and what new challenges would we have to face? It's a lot to think about. And if you're interested in diving deeper into this, we highly recommend checking out the research paper we've been discussing. It's full of fascinating details, and it really gives you a glimpse into the future of secure communication.
Yeah, it's a must read.
Definitely. Thanks for joining us for this deep dive. We'll see you next time.